2.7 about inequalities. Inequalities. But what's harder about the inequalities is, look at this example. It's a nasty polynomial. Obviously, it's harder. We did like a really easy one on the board, I think, on Friday when we introduced this idea. If it was just x plus 3 less than 0, no big deal. Subtract the 3. But why can't we just add the 6 and be done? Well, we still have x squared and minus x. We can't put them together. They're not like terms. So then we're like, well, we can factor. We can pretend this is an equal sign, and we can factor, but we can't get x alone. So what we saw is that when we do factor, we can find these numbers called key numbers. And I think we talked about key numbers on the page before. If you looked at your notes, key numbers for polynomials are the same thing as the zeros. So we go ahead and take a polynomial, we find the zeros, and then we put those zeros on step number 2. Oh, actually, step number 1. Where do we put the key numbers?
Number line.
On a number line. And once we put them on a number line, we've now split the number line into however many intervals are in between or on the sides of the key numbers. So there's one interval from negative infinity to negative 2, another interval from negative 2 to 3, another interval from 3 to infinity. I kept all of these zeros open because, am I allowed to have the values equal 0? No. What if this was a less than or equal to, what would I change?
Bracket.
It'd be a bracket with all of the zeros. Okay? So they're parentheses because it's not or equal to. And now the name of the game is test 1 point in each of these intervals. And so I chose to test negative 3 because it was close. I chose to test 0 because I thought it'd be easy. Could have plugged in 1 or negative 1 or 2. And I chose to test 4. So what did I do with these 3 test values? Where did I put them? To the original polynomial. I plugged them in and I said, hey, what do you equal? And then I asked the question, is 6, which was the final answer when plugging in negative 3, is 6 less than 0? And the answer was no, so that's not part of my solution. Negative 6 was less than 0, true, so that whole interval is going to be part of my solution. And then positive 6 was not less than 0, so no. My final answer was just that one interval, negative 2 to 3. But what changed when I went to this example? Okay, I have an or equal to. So you guys see how I had, I put some brackets. I didn't put any brackets down here. Let me help just for a second. Or equal to means my 0 could be included, which means I should have put brackets around the 8s. So if you want to change that, that's a good idea. I think I added the bracket at the very, very end. The 8 could be included. The 0 could be included because of this or equal to. But why do I keep the 5 with a parenthesis? What's special about the 5? It's undefined, so it doesn't matter. It can't work. It does not even exist. So I have to keep the 5 open because he's a discontinuity. He's a place where the domain cannot equal. So the 5 has to stay a parenthesis. But the or equal to allowed the 8 to be included, which is why my final answer has a bracket around the 8. However, when we found our key numbers, was I able just to, what was the hint for the rational? Isn't that in our notes somewhere? Did you guys find the hint for the rational key numbers? So at the top equal to 0 and the bottom equal to 0, but only when you have what on the other side? 0. What did I not have on the other side for this one? I didn't have a 0. So I didn't just set the top equal to 0, bottom equal to 0. That wouldn't work. Instead, can you tell what I did do? Let me zoom in. There's a lot of math on this page. To find the undefined, that part's easy because you just look at the denominator. To find the undefined point, zeros and undefineds, I just said, hey, that's at 5. So the undefined looked in the denominator, that's at x equals 5. But for the other one, I had to pretend like the less than or equal to was an equals. I multiplied this to the other side. I just solved. I solved until I figured out that x was equal to 8, and that was my other critical, or my key number. So for the undefined, steal the denominator. For the other critical number, solve as though there were an equal sign. But once I get those key numbers, I put both in my number line, I test 1 point in each of the intervals that are formed. I figured out this middle was totally false. That 5 is not less than or equal to 3. Looking back at the beginning, I had to compare after plugging in to less than or equal to 3. This one was true, that one was true, so both of those form my answers up above. Okay, that's section 2.7. This is the homework you were supposed to start over the weekend before you went on retreat. Seniors were working on it on Monday. As they were waiting for you guys, they kind of had a nice weekend off and were able to work on Monday. But we did need to do a couple more examples. So, here's one example. We're going to do a couple examples. And this is, if you guys noticed, this one's from the 50s and the next one's from the 60s. So it's the end of homework. It should be after you got through and got a good idea of what was going on. Got to practice the basics, but some were harder than others. Then the directions get kind of funny. And they get kind of weird. This one says use a calculator to figure out an inequality. What does that mean? Well, if you're supposed to graph it, where would you guys put this? In your y equals 9. Good. And if you were to graph it, can I show you the picture so we don't have to get our calculators out? This is the picture. And you're allowed to approximate the values. The key numbers are the zeros, right guys? Can you see, just from the tick marks, can you approximate? This is a 10 by 10 standard window. From the tick marks, what would you think the zeros are, approximately? Good. So we can approximate from the graph our key numbers of -1 and 3. And if it helps, you can still think about a number line. And you can still think about -1 and 3, but we can use the graph to maybe do some of the work for us. For instance, what's my inequality saying? I want when y is less than or equal to 0. So if it helps, you can plug in the function. So my question to you is, if I was to plug in, or if you were to plug in -2, what y would you get? One that's greater than 0? Less than or 0, or equal to 0? Less than 0, because you guys see the y value that goes with -2? Isn't it below the x-axis? And aren't all the points below, aren't they all going to have y's that are negative? It goes down. So at -2, I can say, oh, hey, cool, you know what? -2, when I test it, this one's going to be a check. This interval is going to work. But what happens if I plug in 0 or any of these points? What are all of their y values since you go up to them? Well, I don't want positive. I want less than or equal to 0, so that's going to be a no. And what's going to happen when I plug in 4 or 5 or 6? Down, so it's going to be less than or equal to 0, check. So you can use the graph to say, oh, hey, what would I get when I plug in? And if you look at the intervals, we got checks on the interval to the left of -1, which would be -infinity to -1. Ooh, bracket or parenthesis?
Bracket.
Because it is allowed to equal to 0. It is allowed to hit at the 0. If you want to be super snazzy with math notation, you could put a U, it means union, or you could just put a comma. That interval is true, and what's the other true interval up there? Bracket with 3, 2. The graph does go down to -infinity, but remember we're doing the x's, and so the x's on the number line would be 3 to +infinity. Now here's another way of looking at it on a graph. You could just say, hey, what portions are below? Oh, those two are below. Cool. So -infinity to -1 and 3 to +infinity. What if the inequality were to switch and say greater than or equal to 0? What would I choose instead?
The middle.
The middle one, because that's where it's above. So if you're looking at a graph, you can look at the below or the above to tell you less than or greater than. That's the point of the problem. And it makes everything faster. You don't have to do the test points or plug them in and do the math. So it is helpful. So with inequalities, just think less than means below this y height, which was the axis in 0. Greater than would be above the y height. And then the or equal to is whether or not you close the interval with brackets. Okay, that's one type of example. I wanted to do one more. That was from the 50s. It got kind of funny with the graphing calculator. Here's the other funny one. And it's funny because there's no inequality in the problem. So why on earth is it in this section? Some of you have already figured it out if you tried homework, looked in the book, looked at an example. There's no inequality in the problem, so why on earth is it in the inequality section?
Because there's a range of things that X cannot be.
There's a range, I would say a domain, but yeah. There are intervals that X cannot equal, and there are intervals that X can equal. But why? What's the domain problem? What's causing the problem? The square root, good. What's the domain of square roots? What are we supposed to do with what's under the square root? Close, we don't want it less than or equal to.
Not equal.
We want it greater than or equal to. Remember, what's under a square root needs to be positive, not negative. If it's negative, it's imaginary, that's bad. It's allowed to be 0. Remember, what's not allowed to be 0 is a denominator. But a square root, it's allowed to equal 0, but it cannot go below. That's back to the domain problems, chapter 1. I had you start and highlight it, and hopefully you did the domain problems that show up in functions. What's under the square root has to be greater than or equal to 0. So, did they show us the inequality? No. But they gave us a function that we should have or should learn to connect to an inequality. So now that we've talked about the domain problem, guys, we have a problem with an inequality. So let's review. What do you do when you have a polynomial greater than or equal to 0? First step. Solve for x. Pretend it's an equals, right? So key numbers. Pretend it's an equals. Solving for the zeros. 2 is one of them. Plus or minus 2 is what x equals. 2 ways to get there. Add the 4, plus or minus square root, or factor. Whether you factor or whether you add the 4 plus or minus square root, don't you get key numbers of plus or minus 2? What do you do with those key numbers? Step number,
Put on the number.
yeah, it's technically still step number 1. Put in the number line. And we've now split our number line into intervals that we need to test, right? What would be the interval over here on the left that we're testing? Bracket or parenthesis?
Bracket.
Because or equal to. Does that make sense? Okay, the middle interval is just going to go from, you guys already told me brackets, good. No undefined points, but good. Or equal to. Last one? All right, time to rock it. What's some point you want to test to the left of -2 for this interval?
-3.
Yeah, I think -60, you go. Go team, go. How about in between?
0.
You could do 1. 0 might be faster, but either way. 1 or 0. Both of them are going to work or both of them are not going to work. It's okay, just pick one. And what's something to the right? Trace them. What do we do with each of those? Plug them in. You can either plug them into this or you can plug them into that and say real or imaginary. If it's real, sweet, that's part of my answer. Imaginary, nope, it's not. I'm going to go ahead and just plug it into the very, very beginning. So, square root of -3 squared minus 4. Wouldn't that be the square root of 9 minus 4, which is 5? It's not pretty, but is it real? Yeah. We can ask, is 5 greater than or equal to 0? Yes. So therefore, this is a check. We'll keep in hand. Middle one. Let's plug in that 0. Square root of 0 squared minus 4 is the square root of -4. -4 is not greater than or equal to 0. This is imaginary, therefore not part of the real domain. Maybe some of you can already figure out what's going to happen with this guy. Real or imaginary? Got it. So therefore our final answer is going to be domain. X is going to be within, parentheses for infinities, right? Negative infinity to -2. 2 to infinity. Dun, dun, dun. Tomorrow we're going to grade this homework with the evens. I basically wanted to cover 2 more examples before I graded the homework, and I was trying to give undergraduate and sophomores, juniors a chance to have tonight to finish it up, okay?
So would the answers be negative infinity?
So it's the whole intervals. It's not just 1 or 2 or 3, it's the whole intervals of the answers, okay? But we have to leave them out. All right, cool kids, if you look on the backboard, our goal was to finish section 2.7. It was not on your test because of timing, like it just wasn't gonna work out. If you guys thought about it, I could have given you the test today. Think of how ready you would not have been.
Yeah.
Tomorrow is the Great California Shakeout, so some of the classes are shorter, so that wouldn't have been good either. And then if we wait until Friday, it's even worse. So, anyway, we took it last week, for better or for worse. You're gonna get it back. Corrections are gonna get you 1/3 points back, but let's talk about that test tomorrow when you guys have it in your hands. For right now, we are starting according to the board, section 3.1. Huh? So you guys are updating your table of contents. P.S. Go to your homework spiral, chapter 3. Figure out what page chapter 3 is going to start on. Some of you did not do that last time for chapter 2, and I was being gracious and not taking off points, but I will take off points next time. So, homework spirals, chapter 3. Table of contents, chapter 3. And for anybody who did not get 100% on their note check on Thursday, you gotta keep that table of contents up to date with section titles, title titles, and page numbers. Those are for the notes. For the homework spiral, all you need is chapter 3, the page that the first homework starts on, and you're good to go. Josh. No, you just keep going in your table of contents. Just keep going in your table of contents. But when you go to take your notes, there should be a new page for 3.1. Yeah, but table of contents, just like a book, you just keep going right in order. Oh, the chapter is called Exponential. Oh, no, I'm so sorry. I think it's called Exponential and Logarithmic Functions. Let me double check. Oh, come on. Exponential and logarithmic functions. Chapter 3, exponential and logarithmic functions. Cool kids. I've heard you say at least a couple times this year, like, oh, that's how you're supposed to do it. It's okay. We'll do that with this too. All right? What I want you to think about, basically the whole chapter, exponential and logarithmic functions, there are lots of little puzzles. There are lots of little puzzles. Or you can think about them as lots of little games. I like puzzles a little better. But all games have rules, right? Or they should. If you take away all the rules, and stuff gets really nasty really fast. Yeah, no rules is dangerous. So, isn't entire chapter. Lots of baby puzzles. But you gotta follow the rules. You gotta follow the rules. Don't want to get disqualified. So, here we go. Exponential functions and their graphs. Nice thing is we're not even doing logs today. Exponentials.
Awesome.
These functions that we're starting in on are not polynomial. Oh, sorry, last chapter. I apologize. Last chapter, even chapter 1, we were dealing with algebraic functions. Functions you would have seen in Algebra 1. Algebraic functions, those are polynomials, the square root functions, the rational, like the top over the bottom, absolute value. Those were all algebraic functions. You were dealing with x's to different powers, basically. And even the square roots, that was like x to the 1/2. But what we're starting in on this chapter, they're called transcendental. Man, I cannot spell. Oh no, I was right. Transcendental. There we go. Transcendental functions. They transcend. That sounds nice. Now you're going to have special functions in terms of x, but they're not going to be directly powers of x. They're going to be like e to the x, or ln of x, or log base 7 of x, 2 to the x. X's are still involved, but they're not the main players, we'll put it that way. Then we'll get into sine of x and cosine of x, and man, there again, x's are involved, but they're not the main players. That's just an introduction to what we're doing in chapter 3 and beyond, but let's go ahead and start talking about an exponential function. And if you have your calculators, grab it out. Let's make sure that you know how to do an exponential function in your calculator. And have it ready. Most of you already do, but just in case. But first of all, let's name what's going on. A is who we call the base. And it's going to be a constant. For exponential functions, you have superscripts, just like you did with polynomials, except this time the x is not down below in the base and the numbers in the powers, the numbers in the exponents. Instead, the variable is in the exponent, the constant is in the base. The variable is in the exponent, the constant is in the base. What button in your calculator, if you've already gotten there, is going to help you with letters A and B? If you need to raise 2 to the power of each of these different values. You have a little caret. You guys know where the caret is?
No.
Right above the division.
It looks like an up thingy.
Do a little up arrow.
That is not fair.
Oh my goodness. It's spelled differently. C-A-R-A-T.
Okay, caret. Does that help a little bit? That's okay, because a lot of you guys in your head, when I said caret, you were thinking C-A-R-R-O-T. A little bit different. We're doing 2 to the power of. We gotta plug it in. So it's 2 to the power of negative 3.1.
But
Which would be the same thing in your calculators as 2 with a little caret of negative 3.1. And what did you guys get as your final answer? 116.
0.7.
Ah, if we round it properly. Okay, because 3 decimal places.
Sorry, guys.
All right. Question. This doesn't make sense. 2 to the power of, why is it tiny?
Because it's a negative.
Ah, it's a negative exponent. How do negative exponents work differently than positive?
It's 1 over the...
Good. I want to remind you guys quickly that you're dividing 1 by 2 to the power of. So 2 to the 3.1, why doesn't somebody find that for me? What is 2 to the power of 3.1?
Well, then you just use the arrows.
8.574.
8.574.
Nice. Okay, so pause. 2 to the power of 3.1 is 8 point something. 571, something like that. This is a bigger number, except it's 1 over that, and so 1 over 8 point something, yeah, it's going to be a small number. 0.117. So when you have a negative exponent, it is going to be a small decimal. However, letter B, what's going on? Can we raise 2 to the pi? What's going on there?
You're going from 1 to 6. What?
Yeah. So when you plug in 2 to the power of, go find the pi, isn't that second something? Second Garrett?
No, don't. Are you kidding?
Before you guys hit the enter button, is it going to be a big number or a small number?
Small number.
Big,
I'm
small
lost.
number.
It's
Small, because it's a negative again. Even though it's a pi, it's still a negative?
Oh, negative.
I'm stuck at 1.113.
Yeah, it is going to be 0.11.
Oh, babe.
3, is that how you round it?
Yeah.
Cool. So, most of us think if you're raising something to a power of, if you're raising 3 to the 4, or 4 to the 2, or 6 to the 12, it's going to be a lot bigger, right? But remember, when you have negative exponents, they're going to get smaller because it's 1 over 2 to the power of the positive. Okay, that's the beginning. Let's talk about graphs. That's the beginning. Let's talk about graphs. Okay, exponential functions, not a polynomial. Not a polynomial. All right, hang in there. The most basic exponential function, we need something to the x and we need a constant. Why wouldn't I do 0 to the x? Yeah, 0 to the 1 to the 2 to the 3, it'd all be 0, 0, 0, 0, 0. Well, that's boring. Nothing's changing. Okay, cool. So 1 to the x, that must be the most basic one.
Still more.
1 to the 1, 1 to the 2, 1 to the 3, 1 to the
Two.
4. It's all going to be 1.
Let's
So,
do 2.
no, 2. That's what I want. 0 isn't going to be a good base. 1's not going to be a good base, which is why we say for exponential functions that technically a needs to be
2.
greater than 1. Well, let's put it this way. A needs to be greater than 0, but a cannot equal 1. Another way of saying it is a is going to be in between 0 to 1, 1 to infinity. Now that's not super important to memorize per se. I just want you guys to realize why you're not going to see 0, why you're not going to see 1. So 2 to the x is pretty much the most basic exponential I can show you. Let's talk about a couple things that we know. What is going to be the y-intercept when x is 0?
0.
Careful, plug in 0, and anything to the 0 power is
1.
Okay, so any basic exponential function, whether it's 2 to the power of, or 3, or 4, or 5, anything to the 0 power is 1. Which means
0, 1.
all exponentials that have not been transformed are going to have a y-intercept of 0, 1. Now, I'm going to do one more special point. Well, let's do 2. If I was to plug in 1, what's 2 to the 1?
2.
Yeah. And then what if I was to do negative 1? What's 2 to the negative 1? Pause. We know negatives. It's 1 half over.
2.
So 1 over 2 would just be 1 half. This is actually going to be true, guys, of any exponential function. But what I would need to show you to make it general is if we had y equals a to the x, as long as a is not 0, is not 1, I could graph and say, hey, 0, 1, yep, put that in the bank, we got it. 1 is going to be at a, whoever a is. This one it was 2, because that's my a. But at 1, I'm always going to have a, and at negative 1, I'm always going to have 1 over a. So any exponential function is going to have a y-intercept at 0, 1. When x is 1, it'll be at a. When x is negative 1, it'll be 1 over a. Always going to be the case. Those can be like our 3 representative points. Domain, whether you're looking at a general one or a specific one. How far left does it go?
Infinity.
Infinity left, which is negative infinity, and then how far right does it go? Yeah, it's going to take a while to get to positive to infinity, but it's going to keep on, there's no asymptote, it's going to keep on expanding. It's just going to take a really long time because it's going super, super high, super, super fast. How low does it go?
Above, almost to zero.
Almost to zero. What is existing at
Horizontal
a
asymptote.
horizontal asymptote? So therefore, I'm going to have an open cutoff at zero. It's not actually going to hit zero. It's going to get closer and closer and closer. And how high is it going to go? Infinity. I'm going to change this blue one to be the same color as the rest. Strictly monotonic just means that it's strictly going one direction or behaving one way, which it is. It's strictly increasing. Strictly increasing, only going up. And it's going up very, very fast. And we already talked about the horizontal asymptote, and where is that at?
Zero.
And last but not least, nothing to fill in, I'm just saying it's continuous. There are no breaks, there are no jumps, there are no vertical asymptotes that it needs to like go over. It's continuous as well. Now, these are the general characteristics of a parent function. I'm going to make this blue just for sake of illustration. Question, this is a parent function. What can we do to transform here? How do we change up functions? We can add or subtract to shift, inside or outside. We can multiply or divide to stretch or shrink, and we can multiply by negatives to flip. So can we transform? The answer is yes. Can we transform? And the answer is yes. I'm not going to go through all the transformations. Some of them we'll kind of deal with when we get there, but I will talk about shifts, translations, and reflections. We'll talk about shifts, translations, and reflections. These being added on the outside. Wouldn't that be a vertical shift? These being added on the outside, so it'll be a vertical shift. A is the base, and maybe we'll talk tomorrow about what the base does as it changes. But right now, let's put the base. You guys, C is being subtracted on the inside. So what's that going to be? Horizontal shift. Then we just need to remember, if we need to go across the x-axis, flip what's up to go down, what's down to go up. That's going to be a vertical flip, and we'll talk tomorrow about how that will look as a transformation. And then across the y-axis, what's right is left and what's left is right. That's going to be a horizontal flip. What is your goal tonight? Finish 2.7. If you want, maybe start on 3.1, but we're going to finish 3.1 tomorrow, maybe even get to 3.2 if we're really lucky. The kiddos catch up, that's the goal. All right, graduate bell, time to go to chapel, I'll see you guys in there. If you have any questions, come see me after school or during lunch, you should be in here both days. Great job, Edith.